All right. Welcome to the Brakes New Member lecture. Thank you for coming. My name is Matt Jeffries. I'm the Brakes lead this year. Let's get started. All right. So anybody tell me what brakes do? This is kind of like a broad question, but does anybody have like what they think they know is the answer? Anybody? Come on. Okay, stop. How do they stop the car? Okay. What is that? Does anybody have any other, like, how do they stop the car? How do the brakes stop the car? Does anybody know? Anybody have it? Yeah, there you go. So you take the kinetic energy of the car, you turn it into thermal energy, and that energy goes into the rotors. So we use friction to do that. The basic kind of way the system works is take kinetic energy of the car, like I said, put it into thermal energy in the rotors, and then that is the entire system is limited by the grip of the tires. So a lot of the vehicle dynamic systems like suspension, brakes, chassis a little bit, everything is limited by the point of contact with the ground, which is the tires. And then there's a difference between how you brake in a race car and how you brake in your car when you're driving. Kind of just cover a little bit of how that goes into the design of how we do brakes versus they are on like a traditional car. Let's go into, all right, so kind of some of the dynamics of braking. Like I said, the grip is what connects the car to the ground. So everything that the car does goes through the tires, more or less. So what affects the grip of the tires? So the way we find the grip on the tires is we start with the static weight of the car, which is how much of the weight is on each axle of the car, right? So if you have your engine all the way in the front, you know, you're gonna have more weight on your front axle versus your rear axle. Ours is kind of somewhere in the middle, so we end up having, I believe it's 48% front weight. So there's a little, 52% of the weight of the car is on the rear axle when it's not in an acceleration event. So then when you accelerate your car, or in our case, I guess, decelerate, you end up shifting some of that weight from one axle to the other. So we calculate this to determine what braking forces we can apply at which axles and which wheels. So when you brake on your car, your weight shifts forward, which is why a lot of the components in the front of the car, the front braking components, are much larger than the rears. You can apply a lot more braking force because you have more grip at the front of the car when you're braking. And then downforce, so aero plays a factor into how you can, the forces you can apply and the braking. So the more downforce you have on the car, the more grip you have at the tires. So this means that you have the most possible braking power when you're going the fastest. So you kind of look at the difference between when you brake in your car, right? So you're coming to a stop sign or whatever, you kind of press slowly because you don't want to jolt the car, and then you kind of press on the brake heavier. When you're racing, you want to press that brake as hard as you can initially to get the most braking power out of your faster speeds, and then kind of let off. So this is the some pressure data from a test session. You can see the driver jams on the pedal, which then spikes the pressure and then slowly releases off. So this allows you to have the most possible braking power going into a corner or slowing down. You can slow down the fastest by pressing on the pedal as hard as you can while you're going fastest because you have the most downforce at that moment. So these are the rules of our system. These are the basic ones, you know, the big ones we have to kind of design around for the most part. So braking systems, they have to act on all four wheels. You have to be operated by a single control, and you have to be capable of locking all four wheels. In addition to that, you have to have two independent hydraulic circuits so that if the one circuit fails, you still have braking power available on two wheels rather than losing all your brakes if you have one broken line. And then you cannot brake by wire, which is, if any of you guys are familiar with like boats where fly-by-wire is basically you have your throttle is a sensor that reads data, and then that does the throttle for the boat or the braking on its own. We basically have to have direct connection between the control and the brakes instead of a electrical connection. Those are the rules. So this is kind of what the brakes have to do. Obviously, to stop the car. So we need to design rotors that can handle the temperatures of converting the kinetic energy of the car into thermal energy. And then we have to size the two master cylinders for the two circuits accordingly to basically maximize your braking pressures or your braking power. And then we have to ensure that all the components are rated for the pressures that you see with the master cylinders you chose. So the other systems that we work with are a lot of the other vehicle dynamic systems. So we work with Cockpit because they make the brake pedal, and then a lot of the stuff in the cockpit we run lines through, stuff like that. We work with suspension a lot because the braking components are on the uprights. They have to deal with how they design their stuff, kind of impacts how we design ours. And then electrical, pretty much everybody deals with electrical. Everybody's got sensors. And then we have something else that we deal with later that electrical does work with. I'll talk about that in a minute. So here's some of the components of the car. So we have master cylinders and calipers we get from Brembo, one of our sponsors. And then we create, design and manufacture custom rotors. So they change from year to year most part. And then the big part that makes our system different from other teams is we have an ABS unit. So this basically I'll talk about in a minute, but it's really kind of what separates us from other design teams in SAE. And then we run hard lines and soft lines, which basically is how you route your brake pressure from master cylinders to the ABS and then to the four corners of the car. All right, so to determine what components we use on the car, we need to do some hand calculations, kind of determine what we were talking about earlier with some of the dynamics. So we're going to start with these basic assumptions here. So 430 pounds is the target car weight this year. And it's about 580 pounds with the driver, depending on which driver you have. And then you have your CG height, wheelbase, target of deceleration at a certain speed. So we use that to determine kind of aero data, stuff like that. And then your size of your rotors, the static percent weight, aero assumptions. I know it's at 35. I got to fix that for 60 later. But your pedal ratio, and then the rolling tire radius. So then we use these to calculate the things we need to determine to decide what components we use. So starting with the static weight, you use the percent weight times the total weight. So you decide that kind of breaks down how much weight is on each axle. So that's kind of, you see 278 pounds on the front, 301 on the rear. So you can see we have a little more rear weight than front weight because our motor is like a little farther behind, like the center of the wheelbase. And then you calculate the dynamic weight transfer. So this is when you're pressing on the brake and you're moving forward, it's how much of that weight transfers to the front axle versus the rear. We use this equation. You get about 219 pounds that shift forward at 2.2 G deceleration. And then you calculate the grip. This is a very simplified tire model. And this calculates kind of how much grip you have on your front and rear wheels. And then we use that to determine the torque required to lock each the front and the rears. So torque is distance times perpendicular force. So we use the grip, which is the frictional force that between the tire and the road, and then the radius of the tire, and that yields the torque that's required to break that frictional force, which is the torque to lock the fronts and the rears. This is kind of what we designed the system around. It has to be able to do that per the rules. Of course, our ABS unit doesn't do that when we race normally. So from here, you calculate the system pressure. This kind of comes in where you determine which master cylinders to use. So when you have master cylinders that you're going to use, do these for a couple of different combinations of the two. But you have your pedal force divided by 2 because you have 2 master cylinders, multiplied by the pedal ratio, which is how much of the force that you're pressing on the pedal goes into the actual master cylinders. So then you get about 268 pounds by pressing on the pedal with 80 pounds of force into each master cylinder. So this is then transferred into using the torque that you calculated earlier to determine how much we need to lock. And then you multiply this by basically finds the pressure. That's the force that you're inputting into the master cylinder times the area of the master cylinder. And then your pressure at the 80 pounds comes out to about 1,400 PSI in the front circuit and about 1,000 PSI in the rear circuit. So this is when you press it 80 pounds with the master cylinders we have in the car at the time. That's the pressures that it takes to lock the wheels with the ABS off. And then so this is the torques that they yield when you go back and you do the torques. Wait, what is this? Yeah, so this is, you can see this is the components we have on the car, and then this yields torques that are higher than we calculated before, so it will lock the wheels. So what does all this mean? Basically, doing all of these calculations, you get the torque to lock values, which is what you have to design your system around more or less. And then you have a couple of biases. So your dynamic weight bias, so it's 80% of the weight of the car is in the front when you're decelerating at 2.2 Gs. So from there, you can kind of think and relate that to how much of the torque that our system provides should be allocated to the front versus the rear. So with what we have right now, 72% of that is given to the front versus the rear. This is kind of a product of what the calipers and the rotors that we choose, how that relates to the torques that they apply. And then the pressure is also driven off of the master cylinders that we choose, and the size of the pistons in the calipers that we choose in the front and the rear. So this is kind of what we use to decide what we use on the system. Yeah. Any questions about the calculations or anything like that? Nothing? All right. So this is kind of diving more into which components we use. So like I said earlier, we use Brembo calipers in the front and the rear. A lot of the components we use are motorcycle components. So these are motorcycle calipers. These are the fronts. Those are the rears. As you can see, the rears are a lot smaller than the fronts. I don't know if it's easy to see from here, but in the shop, fronts calipers about that big. Rears are much smaller. So we get these sponsored from Brembo, but because they're motorcycle parts, you can see this one, this is the bleeder cap, which is how you bleed the brakes. It's on the top because this is on the left side of the car. That one over there, I can't get my shadow over there. Bleeder cap is upside down because motorcycle parts are not meant to be flipped. You know, there's only two wheels on a motorcycle, so they just make them the same side. So when we bleed, we have to take these calipers off, flip them upside down, and then bleed like that. Pads. So this has kind of not necessarily been a mystery on the team, but we haven't had a lot of validation data for why we use what pads we do. So there's a couple different kinds of pads. Pads, organic pads, and the metallic pads. Really, we look in the difference between sintered and organic. The difference between the two of them is, well, how you make a sintered pad is metal powder that is sintered, so it's welded together, and then that is welded to the back of the plate. So these ones here, they got tape on them, but you can see there's the plate, and then it's welded to the other side of that, whereas organics is a powder that's encased in resin and then riveted to the back. So you see there's a little difference between those. The difference in these pads is sinter pads will have a little bit stiffer feel, and the organic pads will, give a little bit more. This makes a difference in how the driver feels when he presses on the brake. How quick does the brake act? Having a little bit of compression in the pads changes that a little bit. So that's an advantage of the sintered pads. The organic pads have a higher coefficient of friction, but they wear a little faster. So you have kind of a trade-off there. And the metallic pads is just a metal piece that's bonded to the plate. We don't really use those, but that's what those are. So this year, a lot of kind of what we're doing is have a project we're talking about at the end that we're going to use to validate why we should use different pads and why we use the ones on the car. So talking about that, pad fade is the relationship between the temperature of the rotor and the pad and the coefficient of friction. So in determining how this changes can kind of set where we want to have our maximum temperatures that we see in the rotor. So it's kind of one of those things you consider when, okay, how large can we make the rotor? How much temperature can we have? Like, how hot are they allowed to get if this is a limiting factor? So we don't have a lot of data for this on the team right now. As far as what it is, basically, as your rotors get hot and you're driving the car, doing multiple laps slowly, if you have a high pad fade, your brakes can start to feel weaker and weaker as the rotors get hotter and hotter, which is obviously not good for lap times. So kind of considering why it's not necessarily a horrible thing, if you have rotors that are a little bit smaller in mass but cool quicker, as you press on the brake, like I said earlier, you jam on the brake when you're going into a corner. Because you have that pad fade, the rotor is heating up, or because of friction, the rotor heats up, and then as it heats up, your coefficient of friction can decrease a little bit, but that's not necessarily a bad thing because you're coming out for the brake after your initial braking effort anyways. So that's kind of something to consider in what you see in the rotor design and your pad choice. In the master cylinders, this is kind of another big thing that makes a lot of difference as to how the system feels. Like I said earlier, we have to run 2 hydraulic circuits. So we have 2 separate master cylinders, 1 for each. And the difference between them kind of determines the characteristics of your braking on the car. So a larger master cylinder will have less pedal travel, and then we see lower system pressures, but will require more force inputted to lock the wheels, whereas a smaller one will have the reverse. Currently on the car, we have 2 different size cylinders. So this kind of causes a problem because you have that difference in pedal travel, or the cylinder travel creates a difference in how much pressure they produce at each position. As you're pressing on the brake, the bias changes. So I think that's kind of what we're seeing in a little bit of the instability we see in braking in the previous year. So when designing and choosing which of these we are going to run, it's a consideration of, okay, how drastically different should I have them? And the reason for having them be different is because, like I said, you have that transfer forward. You need less braking power in the rear than you do in the front. So that's one of the ways that you can have more bias in the front. The pressure bias affects the torque bias. So having more pressure in the front by having, say, a smaller master cylinder, so you have more pressure faster in the front than the rear, is kind of one of the ways that you can alter how the system feels to the driver and how it works on the car. So we can adjust the bias or the pressure bias of the 2 cylinders. We have a bias bar, you can see here. So that twists, and you can adjust the bias between the 2 master cylinders. You do have to stop the car, go in and do this manually. There's no driver bias adjuster. But that's how we adjust the pressure bias and consequently a little bit of the torque bias using the bias bar. So a little bit into the lines of fittings we use on the car. It's not super interesting, but we use hard lines. This is what look like aluminum hard lines. We bend them to follow the inside of the chassis, and then go to each corner of the car, as well as from the master cylinders to the ABS unit. And then we use soft lines to connect from the corner of the car to the caliper, because the suspension components move, so you can't have a hard line there. Disadvantage of using a soft line is they expand as you put pressure in them, so you lose a little bit of the pressure that you would be putting into the pads and the calipers pressing on the rotor. But it's a necessity because you can't have hard lines that go directly into your calipers. So that's kind of why we use those. We have quick disconnects at each corner. So when we break the system down, it's easy. You don't have to undo all the fittings, just disconnect it from the line. And then we use anodized AN fittings. And then, this is since we switched to monocoque, this is the insert that goes in the monocoque. It's tapped. This one's not tapped, but they're tapped so that the fittings can go screw into them. They go through the monocoque, so you don't have to worry about going around it or however other way you would do that. All right, so this is the heart of the system. This is a Bosch M4 ABS unit. Basically, what the ABS unit does, all of you have them in your cars. When you press on the brakes and it detects that the wheels are going to break traction with the ground, it'll pulse the line pressure so that the wheels continue to spin while maximizing your braking effort. So not really any teams run ABS units in FSAE. It kind of sets us apart. It's a huge driver aid. So honestly, none of us here are professional drivers. Alex might say he is, might be, but the ABS system makes it so much easier for drivers learning to use the car, and then in competition to have confidence going into the corner, knowing you're not going to spin. or lock up and spin out. So basically the way it works is there's wheel speed sensors at each of the wheels, and then there's a gyroscope, and then it uses some of the data from the car, and it determines the slip ratio, which is how much of the wheel is slipping compared to the speed it calculates to the car. And then that, once it detects at a certain slip ratio, it'll start pulsing to each wheel that it calculates doing that. So ours is pretty fancy ABS unit. It's off of a Porsche GT car, and then Bosch has tuned it to the specs of our car. Some of the other teams that run ABS units try to make their own. Ours is fancy and ours is cool. Yeah. It's heavy, so it's about 5 pounds. So they kind of use to say the weight savings that is worth every 5 pounds that is there. And then it's a kind of a complicated thing to set up. We've had it on the car for a while, many seasons, but it's also expensive, but totally worth it. Any other questions about the ABS unit? All right. So getting into the rotors. So the material that we use for the rotors is 4340 steel. Basically, this steel has a high ability to retain strength at high temperatures. Basically, you need this because rotors get hot, and then you put a lot of force into the rotors. If you have a material that is weaker at higher temperatures, you might not have a rotor when you're done pressing the brake. They also have a high thermal conductivity, so this is able to dissipate the heat that you put into the rotor. So like I said earlier, you're taking the kinetic energy of the car and you're making it into the thermal energy in the rotors. And then you need to get rid of that thermal energy for the next time that you're ready to put more kinetic energy into the thermal energy in the rotors. So it's important to have the ability to dissipate that heat into the air around and not into the uprights, which is why we use titanium bobbins, which I'll talk about in a minute. But basically, the rotor temperatures, the way that you design the rotor and the effect that the temperature has on that is a rotor with smaller mass will have a larger convective area. So it'll release the temperature or the heat that you put into it faster, but it also get hotter faster. If you have a heavier or a more massive rotor, you put your heat into it, it doesn't dissipate it as fast, but it can retain more heat overall. So then you have the decision between, okay, do we run rotors that get hotter for longer and then can withstand that heat? And then the other question is, do other components that react with the rotor, can they withstand that heat? Or do you run aggressive geometry and low mass that cools the rotors faster, but can't withstand as high of a temperature? So that's kind of what we look into when we design the rotors. So like I had mentioned, we use bobbins to mount the rotors to the hub. Basically, these are these little rings that hold the rotor in place on the hub. These are made of titanium because titanium has a low thermal conductivity. So this keeps the heat that you're putting in the rotor from going into the upright, which is aluminum. So basically that keeps the heat dissipating into the air rather than into the car. And then they allow for a float. Basically, because the rotors get hot, they expand. And these allow for the expansion of the rotor 0.005 of an inch axially, which is if you can determine it off of this. And then radially is like outside. So it allows the rotors to expand, radially and axially 0.005 of an inch. It's kind of if you understand that, the way I was doing my hands. And then sensors. So this is kind of where we get some of the data that we use to calculate and then that we use to determine and validate the components that we use. We have temperature sensors. Next year, we'll have them on all 4. Well, currently we have them on 3 because we were missing a mount. But we're going to make these mounts. The past year, they measure the rim of the rotor. We've designed these to then measure the face. And then we have pressure sensors. So this is the pressure sensors from last year. These have been redesigned to be a little less cumbersome. We got rid of this fitting, flipped them upside down. But those are the sensors we use to gather data for the most part, other than the ABS sensors. All right, this is the main project that a lot of you will be working on in the brake system, if you so choose. this is the Brake Dyno. So this is what I want to use a lot of, or use this to validate a lot of the components on the car. So like I talked about earlier, we don't have a ton of information about pad fade. This is going to basically give us the pad fade of whatever pad that we put into this. Basically what it is this is what it used to look like. This is not it finished. We're now trying to adapt a gas motor to go here, but it's basically like a mini version of the system that will use one of the calipers and then rotors. You can put whatever rotor we're using to test the temperatures that we see in the rotor, as well as you can calculate the coefficient of the pad using strain gauges on this little upright piece here. So there's calculations that go into determining the data that we get out of this. But basically what I'm hoping to get out of it is the pad fade, temperatures, and coefficients of different pads. So determining which pads we use in the car and then why, as well as kind of helping with future rotor design and seeing that the actual temperatures we see in real life versus sims. But this is the big project for this year, more or less, other than making a working system. Any questions on this? Or I guess, oh wait, never mind. I'll go back one. Never mind. I thought the question slide was after this. Any questions on this? All right. So manufacturing, how do we manufacture the parts that we put on the car? A lot of them are off the shelf, but like items like the lines, we buy the line stock and then bend them ourselves. And then the rotors, like I said, we make those in-house. We have some of these steps sponsored, but we buy, we buy stock of 4340 steel, and then we anneal it, and then we have it water jetted in-house. So we cut out the shape that we want. And then we used to have one of the professors here heat treat it. We've moved to a sponsor that does that for us and then grind it to the thickness that we want. And then we bring it back here and we CNC the finishing passes on all of the edges, as well as some of the manufacturing pieces that need to be CNC'd out. I think I have a picture of that. I'll show you that in a second. Bobbins, we make those out of titanium stock. And then the lines, like I said, we buy stock and then assemble them. So this is kind of some of the steps of the rotor manufacturing. We cut them out, heat treat them. These are the pieces that end up getting CNC'd out, right? So we manufacture them. This is unground, and this is ground to thickness, water jetting, heat treating, and then the CNC machine is the last step that we use to do finishing passes and then to cut out these to the final bobbin locations. All right, so now questions. Any questions? Do people on Zoom? Nope.
For adjusting the bias block, is it like feasible for us to do that like electronically?
I'm not entirely sure. I'm sure there's a way to do it. I know like on Formula One cars, racing, stuff like that, there's a way they can do it. I'm not entirely sure as to how that's done, but we justify not having to do that because we have the ABS unit. So, you know, if you're going into the corner, you know, if you're gonna lock up your rears, the ABS unit will take care of that rather than having to adjust your bias to have the perfect bias so that you don't lock one side versus another or axle versus another. Kind of takes one step out of it. Any other questions? Yeah, go ahead.
So how do we go through brake pads?
Okay, so we kind of go through different pads based off of which pads they are. So like right now we have like 5 or 6 different sets of pads. So we kind of go and see, okay, which pad works best. And then sometimes we end up going through pads because, you know, something will happen to the system, you know. But so then of course, you know, then you need new pads. But basically you do a couple sets a season. We don't necessarily burn through the entire thing, but like we'll just replace it with a different one to see how it works better. Any other questions? Yeah, go ahead. That's a great question. So Kwong is working on the dyno. Basically, from my understanding of it, is it's mostly all design and half made. This week, we're gonna try to get all the pieces together and try to like mock put it together, see what we're missing, see what needs to be redesigned, and then work from there. We have all of the components. We just need to put it together and see what inevitably will not work and change that. Good.
Why is 28 on the breakdown instead of a load cell?
I didn't design it. It's a good question. I think the reasoning for it was they were going to use a calculation for this shape in the known material to determine the force that the caliper receives by the reactive force of the friction on the rotor.
A load cell is basically a pre-made block strain gauge.
It might have been a manufacturing thing. I don't really.
Because, well, like they will do the same thing.
Mm.
But also you don't have to do the wiring or any kind of thing. You don't care about weight there. It's just-
Yeah. I don't know. It's a good question.
String gauge.
Yeah, this is just how it was. This has been, I think this was made, I want to say like 2016-ish. So this is how they did it then. And then Cole was working on it last year. I think he just wanted to have it work, not necessarily adapt too much on it. So that could be why he just left it there. Otherwise, I don't know. I think a load cell would probably work there.
Is there already bonded on there?
Oh, yeah. No, that's already on there.
That's the one.
Yeah.
Very.
Any questions? There's nobody on Zoom. It's kind of sad. All right. Yeah. Good. Yeah.